Sorry for the delay. Hi, I'm Mark. I'm going to talk about work that we did in University of Aberdeen Dundee with Andrea Szymkowiak, Bown, and Kenneth Brown. And Dundee is a bit of history. It's a birthplace of most of the standard visualization formats, like the line graph, the pie chart, the bar chart. All of them were invented more or less there. And it's a good place to talk about visualizations in general, and I'll be talking about scatterplots in particular. Well, let's start with the 2D scatterplots. 2D scatterplots are everywhere. I mean, we use them as a first step in data visualization. We use them mainly, as we found out, to do these, well, three main things: as outlier detection, as clustering, and as trend detection. And that's before any statistical analysis is run. We use 2D scatterplots to just take a look at the data. However, 3D scatterplots are not used almost at all, and that is weird because, I mean, we live in 3D place. It's strange that we don't use 3D visualizations. To me, it was strange. Now, the question is, of course, why do we need 3D scatterplots at all? Maybe 2D are good enough. And here's an example of a 3D visualization that was famously useful in figuring out the helical structure of a DNA. And from the memoirs of the inventors, it was very clear that they only saw the helical structure after they composed physically the model. Before that, it was not clear, and then actually we did an experiment with helical structures. It is very clear in a 3D and completely invisible in any 2D projection. So, and that is one example of trivariate patterns that are only visible in 3D, like helices, like polynomial surfaces, like 3D curves, all these things that are useful, that are in the data. We do get trivariate patterns in the data. We would like to be able to detect them. And one tool is a 3D scatterplot, only it's not used because it doesn't work. And the question is why. So to answer this question, I did a PhD on that, basically. I'm going to talk about the last experiment but in detail, but in short, we found out that 3D scatterplots are really no good for outlier detection. That's not what they're good for. However, if you do manual rotation, if you can rotate the scene somehow, it's better than if it just rotates in front of you and automatically. That helps because it enables interface learning. They are, however, quite good for a cluster detection. Cluster detection in 3D scatterplots is very efficient for human visual system. And the last question we're going to dive into right now is whether being able to rotate it in 3D, just take a complete look and free-form scene rotation, is better than a simplified 1D rotation like that. And we use that InterSense wand as our rotation device because it is very precise. It's much more precise than what we have on the market now. It's not what we'll have on the market in 2 years' time, though. So it's almost commercially available. But the technology, not yet. But as a research grade, is good enough. The task, the stimuli were 3D scatterplots, basically groups of points. If that's a bit too much light, but anyway, can I take it? Yeah, I can take it. The scatterplots were combined in space, so there were either 2, 3, or 4 groups of points of different colors, and all of the groups were just randomly positioned. One of them was positioned on a surface, and you couldn't see that in 2D projection. I'm sure you can. Can you see it in 2D projection? You can't see it in 2D. Good. But as soon as you started rotating it, after some time, you would see that one group was on a kind of cup. It's a 4-dimensional polynomial surface, whatever. And we ran for each participant 2 blocks of several trials. One block was just like that rotation, and one block was complete rotation, whatever you want. Okay? And we measured accuracy and speed, and it was 1 hour overall, so just to say that fatigue was not a problem, hopefully. We had 17 participants. Well, we had 20 participants. 3 of them dropped out, but for various reasons. But we had 17 valid participants for which we analyzed data. Yeah, first of all, I have to say that overall accuracy, we'll see that later. Overall accuracy was about 80%, so we had no problems with accuracy. The speed was log normally distributed, so the main analysis was done on logarithm of time, which I heartily suggest to anyone doing time analysis. It's much cleaner this way. And we did it for correct answers only. So the main analysis, yeah, it's from LaTeX. Sorry. The main analysis was basically a linear regression to log time. The rightmost column is just to show that everything was significant. All the variables we were expecting were actually there, and there are only 2 lines that are of any importance here. The first one is interactivity mode. There is a big difference between 1D and 3D, not in the direction we expected. 1D is actually much faster. You're actually much faster to identify correctly the structure if you're limited in your interactivity. Okay? However, a more interesting picture uncovers when you look at the last 2 lines, which is the block number and the trial number. Training was a factor, and when we started analyzing it by block number, just basically what was the first and the second block, where the participants started with 1D and then went over to 3D, or started with 3 and then went over to 1D, we saw a richer picture, more interesting. That's accuracy results on the left. No big difference, non-significant all through. Just there are some. The interesting pictures on the right, where we can see that if a participant started with a 3 degrees of freedom, just full rotation, full 3D rotation, it was hard. It took long. Okay. And then the 1D improved. But however, if they started with 1D, then the 3D was much faster and easier, almost at the same level as 1D before. So there's obviously some learning effect. Okay, that's clear. There's obviously some learning the interface that is easier with 1D and then transfers to 3D and not vice versa. The weird bit was when I started to write it up, I realized there's no theoretical basis for this kind of learning. It's not perceptual learning. Perceptual learning is just seeing the thing, seeing stimulus over and over again and becoming better at seeing it. No active, no interactive component there. It's not motor learning. Motor learning is becoming faster with your hands, just muscle memory. It's not motor learning. It's not learning the task. Learning task was addressed. We did a good learning curve before the experiment. I don't know, maybe I didn't do my literature research right, but I couldn't find a good theoretical basis in psychology and cognitive sciences for this kind of interface learning. For adapting your parameters, and what you see there on the right is the basically 2D scatter plot of manipulation of angles that people used. And we can see the change from the first block on the left to the second block on the right in their parameters, in how they moved the wand. It's trivial, but I don't know what causes. What's the theory behind it? It would be interesting to find out. So, to conclude, the take-home message is basically that, yes, we found out we can show that 3D scatter plots are actually useful and effective tool for detecting trivariate patterns. If you want to look at your data this way, it's a good idea to do so. We found out that restricting interactivity, in some cases, improves performance. So having the fancy 3D 6 degrees of freedom controller might not always be a good thing. It might be, flashy, but not actually efficient. And we found out that interface learning of this sort, of learning to adjust the presentation parameters to your perceptual preferences, I think should be taken into account into designing novel visualization and general into novel interfaces. That's me. Thank you.
Interesting project. Don't know if you can hear me, but I was wondering if you could talk a little bit about how you thought stereo vision would affect your results. I assume that you did it on a 2D screen, and do you think you'd see the same limited degrees of freedom of input being better with stereo vision?
Right. Well, that was researched before us, the stereo and head tracking. We went for very limited interactivity because we went for what was or will be commercially available. There is data for, I'm not sure, I think from Colin Ware's lab, I'm not sure, I might be wrong, about stereo and head tracking, and stereo is not a big influence, but head tracking is a huge influence in 3D perception. If you can do that and see the picture change, that improves the performance by orders of magnitude, yes. Stereo, little bit, but not that far.